In this lecture, we take an example of solving a slightly complicated problem of radiative transfer between two plates, surface 1 and surface 2. This is emissivity epsilon 1, this is emissivity epsilon 2, and there is a gray absorbing and scattering medium in between, and let's a situation where there is heat generation S dot. And the depth of the plate is d. So, we want to get the full temperature distribution in this medium, and to keep the problem simple, we will use a diffusion approximation. We will treat radiation as a diffusion process, which we had discussed earlier in our lectures, where we said that in the thick limit, we can treat radiation as a diffusion process. And if you recall, we showed that QR can be as minus 4 by 3 K d sigma t to the power 4 by d z. Now, this is the extinction coefficient, which is the sum of absorption and scattering. This is the absorption coefficient, this is the scattering coefficient, and these two are combined to give you the extinction coefficient. Note that in the diffusion limit, the single scattering albedo omega plays no role. So, scattering behaves similar to absorption, and so we have an extinction. So, the role of scattering really is to remove the photon from the path, and it does not play any other role. But this, remember, is in view of the approximation we have made. Now, we also know that the first law of thermodynamics states that dq dz has to be equal to S dot, the heat generation per unit volume. And from that equation we have here, it is minus 4 by 3 K d squared sigma t to the power of 4 dz squared. Okay. So, that is your differential equation. The solving this part is of course fairly straightforward. The challenge comes in when you want to apply the boundary condition. So, now we integrate this equation, that is an easy integration. So, we will get sigma t to the power of 4 a function of z So, variation of sigma t to the power of 4 as a function of z will come out as minus 3 by 8 K into S dot. This is in watts per meter cube, this is in watts per meter squared, same as this units, into z squared, because you have done two integrations, and into C1z plus C2. So, this is the complete solution to the problem, but the key aspect of the problem is to apply the boundary condition correctly. And you recall that in the diffusion problem, it is very important to recognize that there is a jump at the wall. And let us take an example. Take the temperature of the wall. This will not be equal to the, note that T of 0 is not equal to T1 and T of D, the upper wall, is not equal to T2. That is a key issue you must appreciate, that in the radiation heat transfer problems, continuity at temperature is not guaranteed. It may happen in a real problem if conduction plays an important role. In this problem, we have neglected conduction, but conduction is there. It will ensure that the discontinuity near the wall is removed by the conduction process. But in the absence of conduction, you have to allow for the jump to occur. So, when you look at the value of this as z equals 0, this is equal to C2. As z equals 0, this is equal to C2, but it is not equal to T1 to the power of 4. Okay. And then you ask what is the value of sigma T to the power of 4 at the top surface, spacing was d, you recall, and this will come out as minus 3 by k 8 as a dot d squared plus C1 d plus C2. So, we got two results now. We know what C2 is, we need to find C1, and C1 can be, now C2 can be substituted here as sigma 2, so we can cut C1 also. But in order to relate this finally, remember that these two quantities are unknown quantities, these are not known. So, just remind you that this is T2, this is T1, and so there is a temperature jump here, temperature goes like this, and there is a temperature jump here. Okay. So, you must recognize existence of two jumps here, one at the top, one at the top wall and one at the bottom wall. So, this temperature is T of D, and that is not equal to T2, and here you have T of 0, that is not equal to T1. So, we have to relate the T of 0 and T of 2 to the value of the. So, we have to use what we derived earlier called the jump conditions. That is essentially applying the which came from flux continuity. So, this is always guaranteed in any problem. So, although the temperature is not continuous, the flux has to be continuous. And from the continuous flux, we have two conditions which we had derived earlier, if you recall, which is that sigma T to the power of 4 at the top surface minus sigma wall temperature has to be equal to 1 minus the emissivity of the top wall minus half, and QR at the top wall minus 1 by 2k square d square sigma t to the power of 4 d z square. This, if you recall, was derived by expanding everything in a Taylor series and retaining the evaluated at the top surface. Similarly, at the bottom surface, the wall temperature minus the gas temperature at the wall, they are not equal, recall, and this is equal to now 1 by epsilon 1 minus half QR at 0 plus 1 by 2k squared d squared t to the power of 4 d z squared at z equal to 0. So, we have to use this flux condition in conjunction with the solution to the equation that we have just obtained to eliminate these two unknowns. That is, the temperature of gas near the bottom wall and temperature of gas near the top wall are unknown quantities, and they are to be replaced by these quantities. Okay. So, when you do that, you will get the following. You have to obtain constant C1 and C2 in terms of the wall temperatures. Okay. Everything has to be real wall temperature. So, C2 is an easy quantity because C2 was equal to this, right. So, so C2 will be related to C1 also. So, first we solve for C1 and the solution you will get is 1 by epsilon 1, sorry, 1 by epsilon 2 minus half into S dot into D minus sigma T1 to the power of 4 minus sigma T to the power of 4 plus 3 K S dot D squared divided by 8. So, this has come from here and this is obtained from that derivative divided by d plus 4 by 3k into 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, although this is a somewhat tedious and long derivation, it is important to understand the implications here. Let us make sure that in the process of doing derivation we did not make any errors. The best way to check errors in this complex algebra is to look at limiting cases. Suppose there was no heat generation. This problem had been solved earlier in one of the lectures. We did for black walls, but it can also extend all black walls. So, you can see that there is no heat generation, this term drops out, this term drops out, okay, and you are left with these terms, and suppose you took epsilon 1 is 1, epsilon 2 is 1. So, even this becomes simple. You get d plus 4 by 3k, and so this can be related to the problem we did earlier for the case where there was no internal heat generation. Okay. That is the radiative equilibrium problem. This is the extension of that result to the case where radiative equilibrium does not exist because there is internal heat generation. Now, let us look at C2. So, C2 will be related to C1 and C2 will come out as sigma T1 to the power of 4 plus 1 by epsilon 2 minus 1. I am sorry. Minus half, that is the boundary condition requirement, into 4 C1 by 3K plus 3G by 8K, where K is the extinction coefficient, not conductivity of the gas. So, you put all this into the final result, so that we get a feel for the final result. So, that will come out as sigma T to the power of 4 a function of Z is equal to 3 S dot by 8 K 1 minus K Z the whole squared plus 1 by epsilon 2 minus half plus 3 K D by 8 into S dot D minus sigma T1 to the power of 4 minus sigma T2 to the power of 4 So, this is not easy to complete here. Let me just redo this. Write it below so that you can easily see the result. So, plus 1 by epsilon 2 minus half plus 3 K D by 8 into S dot D minus sigma T1 to the power of 4 minus T2 to the power of 4 into 3 K Z by 4 1 by epsilon 1 minus half. The entire thing is divided by 3 K D by 4 plus 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this is a fairly complicated and long derivation. So, it is important to check whether we have done all the things correctly. So, it is always good to look at limiting cases to ensure that we get the correct limiting solution. And one thing which we know well from our previous result is, so we will see limiting cases here. So, to verify that result. So, one limiting case is of course no heat generation. So, this is a case we had really done earlier in our lectures when looking at how to use the diffusion approximation. So, let us see how that simplifies the following result. You can easily verify that. So, the standard non-dimensional temperature in such problems comes out as 3 k z by 4 1 by epsilon 1 minus half divided by 3 k d by 8 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this is a temperature distribution if there is no heat generation. This is your standard radiative equilibrium solution to the case of the optically thick limit, which had been derived earlier. You can simplify further. Suppose further you assume that the two walls are black, that case had also been looked at. So, this becomes half. So, we have this is half. So, you have half plus 3 k z by 4 divided by 1 0 1 plus 3 k d by 8. So, this must look familiar to you, because we had solved a similar problem earlier, and wherein we had shown that for example, if you take z as 0, we have shown that the radiation slip at the bottom wall was equal to half by 1 plus 3 by 8 kappa naught. We had used we had called this at kappa naught, k into d, non-dimensional optical depth, and so we saw that there was a temperature slip at both walls, at both z equal 0, z equal to d, and this numbers exactly match what we had obtained for the case of radiative transfer between two black walls with no heat generation. Now, here we have covered the case of heat generation, no heat generation, and the role of wall emissivity. So, you can see that if the wall emissivities are very low, then these terms become very important, this one and this one. And let us now look at how let us look at the limiting case. So, at the bottom wall we saw it is half by 3 by k d 8, and at the top wall it is half plus 3 by k d 4 by 1 to 3 by d 8. So, in both cases the jump does exist. Now, in the presence of a wall which is non-black, we have two additional terms coming in. They actually can increase the jump. Let us now look at an interesting case where the top wall is black, but the bottom wall is highly reflective. Okay. So, if you look at the case where the top wall is black, this term will drop out, and the bottom wall is highly reflective, this term will dominate, and so will this term will dominate here. So, indeed epsilon 2 equal to 1, and epsilon 1 is much less than 1, highly reflective bottom wall. So, what you will find is that this term drops out, this term dominates, and if indeed it dominates over the term having the extinction coefficient, then the temperature, if this is very small epsilon 1, and so this term dominates. So, this quantity will approach 1, which means the temperature everywhere will be equal to T2, and the bottom wall will play just no role, because if the bottom wall becomes highly reflective and the top wall is black, so the gas is truly radiatively coupled only to the top wall, and so the temperature of the gas will approach T2. This T2, temperature of the gas will approach T2 here, and there will be strong decoupling at the bottom. So, this is not surprising in this example, because if the heat generation is 0, the gas can only get heat from the two walls, and if the emissivity of the bottom wall is very low, no heat transfer occurs bottom wall to the gas. The gas is really radiatively coupled only to the top wall, and the temperature there will approach T2, and there will be a huge temperature slip at the bottom, and so this is not surprising. So, so you find this interesting situation that is prevailing here, where in the absence of heat generation and when the top wall is black and bottom wall is highly reflective, the temperature of the gas will approach the top temperature and will essentially be completely decoupled from the bottom condition. Now, let us go back to the previous thing we derived. Now, let us look at, now having understood that case, let us look at the full problem here, which involves heat generation and it involves heat generation as well as emissivity. First, let us again take the case of black walls, in which this becomes 1 plus 3 kdV4, and this will introduce a half here, and here you will see that now we have to see the relative importance of the heat generation versus the wall induced heat transfer in the medium. And you can see clearly that now there is a new parameter coming in, there is heat generation into D by sigma. This will determine the importance of this term. So, if this quantity is large, this term will dominate and we can essentially ignore this term. And in that limit, if the emissivity of the two walls is small, this will become large and this term will drop out, and you are essentially left with a very simple quadratic expression here. But on the other hand, if the heat generation is small compared to the flux difference between the two walls, then this term drops out, and then you are left only with dealing with this expression here. So, in this more complicated problem, where heat is added volumetrically to the gas as well as heat is coming from the two walls, the relative importance of the internal heat generation and surface heat transfer is driven by this non-dimensional parameter. So, for example, if you are dealing with a problem of conduction heat transfer, problem of combustion heat transfer in a furnace, and you have an idea about the rate of heat generation due to combustion, then by calculating this parameter a priori, you will quickly get a feel for how important the heat generation term is vis-a-vis the wall fluxes. And so, if you take that limit where this term is small compared to this term, then once more you see that then we have to worry about the contribution of this term, which is a constant contribution here. Remember that if this term is small, this portion is not varying with space. So, merely adds a constant value to the variable component here, and then the importance depends upon one more parameter, which is not obvious here, but that is obviously Kd, the optical depth. So, if this is very large, then this term will become small, because this becomes in case very large. So, if this term becomes more important than this term, sorry, this will be small compared to this term, and so again you have got an interesting situation where the temperature distribution is not that the gas temperature is essentially uniform in the bulk of the, except for the sharp drop near the two walls. So, this particular, but a small mistake I signed here, this is S dot. So, this particular consequence is happening in the optical thick limit, and when the internal heat generation dominates over the wall flux, then you find in the optical thick limit the high heat generation inside the enclosure makes the temperature distribution almost uniform, and the effects of the wall is only seen very close to the two boundaries as jump condition. So, this result gives us a lot of insight about the two important non-dimensional parameters in this case. One is the optical depth, that is the extrusion coefficient times the spacing between the two walls, that is one. And as you recall, because you are looking at the diffusion approximation, this it can be useful only in this limit, okay, when Kd is much greater than 1. But the other parameter, the relative importance of the internal heat generation to the wall heat transfer, is driven by second parameter, and so if that parameter is important related to this parameter, then the linear term will play a role, while if this term is small, then our quadratic term created by volumetric heat generation will play a role. So, we see that this kind of interpretation of the solution would be very difficult if this problem was solved numerically. For example, suppose you wanted to solve the full problem without making the diffusion approximation, which limits it to high optical depth. Then you have to solve the full integral differential equation involving essentially 4 parameters. So, let us just highlight that. So, the 4 parameters are emissivity of wall 1, emissivity of wall 2, the optical depth, and the relative importance of stumps. And so the problem would be quite tedious solving for all these 4 parameters, non-dimensional parameters, but remember that finally the interpreted solution which are purely numerical would be much more difficult than that is possible in the simple analytical framework. That is why when solving such complex problems, you do look at the 2 limits first. And then when you go to the intermediate limit where or optimal value, then you go to full numerical solution of the intercodability. There is at that point, but this solution can only be interpreted after you understood the thin and thick limit, because of the complex interaction between the relative importance of internal heat source versus the wall flux, the optical depth of the medium, and the wall emissivities. So, so this has to be kept in mind when looking at such problems. I want to indicate to you the kind of solution we had got earlier for pure radiative equilibrium, in which case the solution was not given this form, but somewhat modified form. So, there we had, in the case of radiative equilibrium, the problem was somewhat simpler because the wall flux was a constant. So, that did not pose any special condition. And so, just to recall that result. So, if you had radiative equilibrium and diffusion approximation and black walls, which is what we covered in the early lectures, the result we got was QR So, this is the result we got, in which we had then we also solved the problem where the wall was not black. This is for black walls. For non-black walls, we extend the result using the wall condition, and that was so you see that you do see some similarities between the solution we have got today with the early solution, and the key point to remember is that the term 3/4 kd or 3/4 kappa naught, as we had called it earlier, was the term which was the contribution of gas vis-a-vis contribution of the surface. And we have a similar result today, identical result today as far as the denominator of the temperature distribution is concerned. And you can actually also compare the heat fluxes. The heat flux, if you recall, the only difference between this solution and the one we got today is that in the radiative equilibrium problem, this is a constant. So, we can easily write it out. In the case of the present problem, radiative flux is not a constant. So, we can write this radiative flux as minus 3/4 K S dot Z plus C1, which we already highlighted. So, in this case, because of the internal heat generation, heat flux is not a constant, it is varying linearly with Z. So, it is not so easy to compare the previous result, but for example, suppose you take QR at Z equals 0, which could be a simple example, that is equal to C1, and that we have readily available. So, let us put that down for comparison, and let us take also black walls for time being. If you do that, you will get the following result, which could be compared with what we got earlier. So, this result you will get for black walls in the present case, and if you compare with what I wrote down in the last slide, you will see that again we will get 1/3/4 curve, that you will get, but you see that in the numerator a much more important role played by the heat source term vis-a-vis the flux term. Okay. So, in the previous problem, the flux term did not play, the heat source term was not there. So, its role was not clearly highlighted, but in this problem you can see clearly the internal heat source term here can become quite important and completely alter even the sign of the flux if it so happens. So, this complex problem highlight that in problem involving combustion, the heat flux at the wall may be controlled more by the internal heat generation term instead of the term involving wall temperature difference. And so, that has to be kept in mind when you solve such problems. Okay. So, with this we come to conclude this discussion about the relative role of internal heat generation versus the wall temperature influence. Now, in the remaining time we will solve another simple problem. Now, so far all the problems we have done in radiation heat transfer involve plane parallel model. But all of you should realize that this is not the only geometry that we deal with in the real world. In the real world, we also deal with the geometry that concerns cylindrical geometry. And cylindrical geometry is encountered frequently in engineering, especially when you deal with internal combustion engines, where a huge amount of heat is released and there is a lot of radiation heat transfer. So, if you want to deal with such situations, you have to now extend the approach you have taken in the radiation transfer formulation to look at the radial geometry. So, I will take a simple case just to illustrate the point. So, in a radial geometry, the first requirement from first law of thermodynamics is that this has to be equal to 0. Okay. So, now we are looking at radiative equilibrium problem. So, under radiative equilibrium, what you have to satisfy is not Q equals constant, that is not going to happen here. And so, from here all of you realize that Q will be equal to C1 by absorbent coefficient. Let us use K here. We consider what we did earlier. So, K into R. Okay. And if you define, okay, let me go back to A, I am sorry, absorbent coefficient under R, and if you define call kappa 1 as A times R1 and kappa 2 as AR2, the two optical depth, that is, you have a cylinder here and another cylinder here. This is R1 and this is R2. So, these are the two optical depths of interest to you. Then again we will appeal to the diffusion model and write Q as minus pi by third d of d to the power of 4 by d kappa, the optical depth. If you do that, you recall that the solution will be plus C2. So, this is quite well known, and so if you want to get the temperature distribution given this one, you can appeal to the, in the true thick limit you can appeal to the continuity of temperature, and you say that at R equals R1, T equals T1 and R equals R2, T equals T2. Then your result will be very simple. You will get a temperature distribution which is log of but if you want to get the heat flux in this case, you need to now appeal to the flux boundary condition that we had discussed earlier in earlier lectures, and if you now recall, the mean intensity G plus 2QR was equal to this at the bottom, and the mean intensity minus QQR was equal to the top condition. And under radiative equilibrium, we know that G is anyway equal to sigma T to the power of 4. That also we recall, and hence substitution of all this into the two equations will give you 3/4 C1 log kappa 1 plus C2, that is the heat contribution, and C1 by 2 kappa 1 will be equal to sigma T1 to the power of 4. This heat flux, this is the intensity. Now, in the other wall, you will get this minus C1 by 2 kappa 1 equal sigma T to the power of 4. Then you can solve for C1 and C2 and calculate the radiative heat flux, and that will come out to be now. What you see here is that in the cylindrical geometry, the problem does get a lot more complex than it does in the plane parallel case, and your only case when you can expect the two results to come close to each other is to look at when, if you recall, this is R1 and this is R2. So, do you realize that when R2 approaches R1 and the gap is very small, you do expect the plane parallel model to work. So, let us see what happens. So, that means kappa 2 rather, yeah, kappa 2 by kappa 1 approaches 1. So, when you invoke that approximation there, this equation now becomes this becomes close to 1. So, that is 1 plus here what you have to do is, we were exactly equal to 1, of course, the problem is not there, log 1 is 0. So, when it approaches 1, so you can write this as K2 by K1 is equal to 1 plus delta K, that is K2 minus K1 by kappa 1. So, this is a small quantity as kappa 1 approaches kappa 2. So, this becomes 1 plus x form. So, it will be 3/4 into K2 minus K1 kappa 2 minus kappa 1 by kappa 1. Okay. And so, this problem now can be this can be thought over the total optical depth, and you can see this result now approaches the one result we had, which is 1 by 1 plus 3/4 kappa 0. So, we see that the cylindrical geometry gives somewhat different result in view of the fact that the heat flux is not constant under radiative equilibrium. So, this I want to reinforce so that it is not forgotten. So, notice that heat flux not a constant, in radiative equilibrium. So, this is the new feature of a cylindrical geometry, that even under radiative equilibrium, when there is no competing heat transfer mechanisms, competing energy sources, you cannot say dQr dz is 0 and Qr is a constant, because Q will indeed decrease as you go from the inner wall to the outer wall, and that is reflected by this expression, and the fact that Q is not invariant influences the final solution, and we get a result which is somewhat different from what we got for the plane parallel case, but we are able to show that in the limit as kappa 2 by kappa 1 approaches 1, then of course we recover that original result. But it is worth remembering that there are other interesting situations here which we could have explored. Suppose the radius 2 was much larger than radius 1, then this term will drop out, now half to 3/4, and this effect will dominate, the cylindrical effect. So, in those problems, like if you want to deal with diesel combustion chambers where there is no R1 really, there is only R2. So, R1 trend is 0. So, this term is going to 0 here. So, then this will dominate your result. So, we took a very simple example of radiated transfer in the thick limit of a cylindrical geometry and showed that there are similarities as well as there are differences. The similarity is in method solution. The difference emerges because of the fact that the radiative flux is not a constant in this case, although we are talking about radiative equilibrium.